Welcome to the webinar series of Enterprise Neurosystem Group. This is the first webinar in the series in which we are going to describe our work on self-describing digital assets catalog. I'm Dinesh Verma, one of the workers on this project and the technical working group chair of the Enterprise Neurosystem Group. In this particular seminar, we are going to describe the activities that's going on in this particular working group, the Central Intelligence Platform. An overview of what we are trying to do will be given by Sharad and Matthew. After that, on the current prototype of the catalog that is built, Anindita Das is going to demonstrate that. This will also demonstrate a first use case. In addition to the use case being demonstrated, the other use cases that the catalog can support in the current versions and which can build upon are going to be discussed by myself and Abhay after Anindita's demos. Towards the end of the talk, we are going to have Josh describe how we are thinking of evolving the catalog in the future direction. With this introduction, let me turn the mic over to Sharad and Matthews. Before Sharad and Matthews take over, I do want to mention that details of this workshop or details of this presentation are available in a published paper which was presented at Smoky Mountain Conference last year, and the links to that are available as part of this presentation. Thank you. Over to you, Sharad and Matthews.
Thank you, Dinesh. Can we go to thanks? So Sharath and I will cover this, and what I will be covering is what's the motivation, what exactly is a digital assets, what the collaboration models could be, and a very simple scenario just to level set so that people know at a high level what's being discussed. So all of us know what digital assets are. They tend to be very diverse, and the listing is provided over there, but it is not only that diversity that causes complexity, they're ubiquitous. And because they're ubiquitous, the distribution has specific challenges. Not only is it a matter of can you distribute it, but can you make sure what is distributed is going to be compatible to where it's distributed. They have constraints in terms of usages. Something may have been working in one given environment because it was trained in that specific environment. Unless the new environment is something similar, whatever was provided is no longer relevant or may have to go through a repurposing or retraining. The timing is important. Some of them tend to be short-term, but most of them tend to be long-lived. So this is what a digital asset is, and we'd like to stress here that it's not just the question of what is the syntax and the format, and how do we make sure we're able to share, and how we're able to update it, etc. But also the challenges related to the semantics of the digital assets. And when we go into a bit more details, it'll be clear to what exactly we mean by some of the challenges. So this is the world that we're dealing with. Could you just go to the next page? Thank you. So here's the world as it is, right? We've got labs, we got different enterprises, they've got all sorts of assets. They run in their own environment. It could be a private environment, it could be out in the cloud, and they'd like to share this information. And how can they collaborate on this? That's a challenge that we're addressing. And to be a bit more detailed, what are the typical use cases that are needed for such level of collaboration? And if once we get into these cases, the next question is, okay, fine, what are the underlying tools and how do you actually make this happen? So those are some of the key topics that we will be covering. So one more, next slide, please. So when we go to the next slide, this is a very simple scenario, but something everyone should be able to relate to. I've got a lab A and I have a lab B. Lab A has a set of models that lab B would like to use and generate a result. Lab A has a lot of data and lab B has additional data. How do the two of them best collaborate and ensure that lab B can get the models and do the appropriate training and get the results? One option would be for lab A to transfer all its data to lab B, and then lab B goes ahead and does the training. But all of us know the complexities there in terms of large data movement. Ownership is not possible. The other option would be go the other way. Let lab B give the data to lab A. Let lab A do the training, provide the model, and then the most optimal model that we probably would do is let lab A train data with the data, provide the model to B, then lab B go ahead and train it. But even that has limitations, right? Because, well, lab B would like now to have the models that lab A has. So hopefully, very simple use case, but provides a high-level overview of what the challenge is. With that, I'm going to go pass it on to Sharath, who will take a deeper dive and be explicit about the problem and other things.
Thanks, Matthews. So the usage scenario that Matthews described highlights the problems, right? So large amount of data is required to generate an AI model, and sharing of this raw data directly might not be feasible, either because of the sheer volume of data or because of the sensitivity with the ownership of the data. So a mechanism to share digital assets is required, and this mechanism to share data must be able to handle the different types of digital assets, such as the training data for machine learning models, the documents containing best practices, policies, and guidelines, configuration files for the systems, and network management, etc. So these digital assets of different types become difficult to use over time because of their formats. They tend to no longer be supported. And also due to just the large diversity in the syntax and semantics of the digital assets, their use both across and within an organization is fraught with difficulties. And digital rot leads to useful data becoming unusable over time. So therefore, a mechanism to share the data needs to be simple, flexible, and extensible. It should not impose too many constraints on what is shared, and it should allow for additional information as needed. So creating an AI model, for example, as the digital asset, for example, an AI model, it can only be used in an operational or an inference environment which is compatible with that, with the training environment, right? The compatibility requirements could be from the type of environment used to train the model. For example, if an AI model is trained in an environment like a PyTorch environment, and the inference environment is based on TensorFlow, the model would typically not work. Similarly, a decision tree or even a neural network trained using scikit-learn will not be compatible with inference environments based on PyTorch or TensorFlow. So while this difference in environment can be handled, there is an implicit assumption that the inference environment and the training environment are the same or compatible. So this implicit assumption, it works fine in some cases during the initial phase of a deployment, but may become a challenge over time. So in many use case scenarios, there may be a multiplicity of inference environments, and maintaining all of them in a compatible manner while upgrading the different versions of different software can become a challenge. So the approach to solve this is by attaching metadata describing the digital assets to make it self-describing. Next slide, please, Anandita. So let's dig deeper into that, right? So what do we mean by digital assets should be self-describing? By that we mean the digital asset should contain metadata that describes what they are, what the usage constraints are, when was it created, what was the training environment, etc. The metadata should cover all relevant items that are relevant to the use case scenario. See, as an example, one has to describe an AI model. One would describe the environment in which it is trained if the focus is getting it into another compatible environment. So that level of self-description would be adequate for the task of model distribution. However, if the model was deployed for a specific task, so for example, let's say it's a visual analysis model of an image, and the distribution has to check that the task being done is compatible. Example, it is not being distributed to a site that is only involved in the task of audio analysis. Then the description of the type of task of the model will be required. And so because of the diversity of the use cases and the needs within an enterprise or a scientific use case, it's very difficult to define a single common metadata format for self-description. Such a standard can become very complex and difficult to use. On the other hand, without a set of common conventions, one cannot hope to obtain self-description capabilities in practice. Thus, we need a standard which is very lightweight, yet it allows easy extension into more complex use cases, which can be customized as needed. So defining a metadata standard is not likely to be adopted if it is done by a single organization. So in order for it to be adopted and used widely, this development needs to be accomplished in an open, collaborative manner across many organizations. Next slide, please, Anandita. So as a result of these considerations, we're developing the metadata standards in an open source collaborative consortium called the Enterprise Neurosystem Group, as Matthews mentioned. In order to keep the metadata specification light, the basic standardization mechanism only asks for the specification of pointers to the digital asset and the smallest possible of common metadata construct. So this also provides the flexibility to extend the metadata on a per use case basis. So using a JSON notation, it consists of the asset pointer. This represents a URI, a uniform resource identifier for a digital asset. And then there's the scope as a DNS format, a domain namespace, which states where the metadata description is applicable. And then there's the type describing the metadata format, and the metadata itself, which is extensible, flexible by definition. And you'll see an example of this when Anandita does her demo next. Next slide, please, Anandita. So we're developing a catalog that can be used to store and facilitate the distribution and exchange of these self-describing assets. The catalog in itself can be viewed as a database of self-describing assets that is accessible via a CRUD interface, create, retrieve, update, delete interface. We also provide a search functionality to the user, which allows the user to search for assets within the catalog. And it's a Python-based REST API with MongoDB, and we have containerized it. So with that, let me hand it off to Anandita for a quick demo.
Everybody. So before I go into that, I'll just show the simple use case that we talked about in the previous slides. So what we'll demo here is that we are simulating Lab A, say, suppose is Oak Ridge National Laboratory, and Lab B is Stanford Linear Accelerator Center. SLAC is a short form. So what we'll show is we'll show the usage of self-describing catalog by showing that scientists from ORNL trains a model and then publishes the model using our this SD catalog backend app. And then after they publish the model, then we'll see that if another lab, says the Slack, tries to retrieve that model, they will be able to retrieve the model and run tests on that model using this catalog. So for this, I'll just show my Jupyter notebooks here. So on this side, you see on my right-hand side of the screen, you will see ONRL, Oak Ridge National Laboratory, will do the training and then will publish it. And on the left side, you see Slack, which will retrieve it and then test the model that is being published by ONRL. Now here we are using a very small model. Here for the demo purpose, we are using the MNIST database, that is Modified Natural Institute of Standards and Technology database. It is a large database of handwritten digits that is commonly used for training various image processing systems. So this MNIST database contains 60,000 training images and 10,000 testing images. For training this model, what we are using, as we are doing it on my local machine, so we are using device as CPU, and we are using PyTorch-based convolutional neural network model that has 6 layers and approximately 1,000 weights. Now we are using 2 2D convolutional layers followed by 2 fully connected linear layers. As activation function, we are using rectified linear units. And as a means of regularization, we are using only 2 dropout layers. For demo purposes, what we are doing, we are only making one pass to the training data. So if I start here, what you will see is I will run this and then it will train it. So we are only doing a one pass through the training data. So as soon as the training is done, we'll see like we can publish this model. So, and also as mentioned by Sharath in the previous, like how we are using metadata for describing our asset. Here you can see we have, it's a very simple at this point, metadata, name of the model, date created, date updated, and also here, as Sharath described, we have data URI, which is the model here, and scope and the data type. Scroll. So here we will publish this model to our catalog. So if I run this and then if I run this, you will see the model is now published. Model name is ONRL model to Slack and the UUID is this. Now, if I'm a scientist from Slack tries to retrieve it, we'll run this and see what happens. So here you'll see that if I search for it, I get the model that was published. That's ONRL model to Slack. Now I'll try to run the test on it, and you'll see that it ran the test and the accuracy is 69%. But the accuracy could be 100% as we are running, like not running it so many times, like training it that many times. That's why the accuracy is 69%. But if we run it over and over again, the accuracy will increase. So now we have all this. So now you can see that if lab A publishes a model, lab B can retrieve it and also run tests on it. And similarly, the other way around, like if lab B wants to share something, they also can publish the model and share it across. Now going back to the slides, I will show the supported APIs. So let me go back to the screen. So the APIs that were supported in that in the demo and also as described by Sharath was the CRUD operations. So here we can publish a catalog, update a catalog. Those are all APIs that are available for the users to use. And as in a couple of minutes, we'll see how in the future we are trying to create CLIs to use these APIs. So I can also demo these APIs as part of just separately. So let me do that. Screens here. Second. So I have scripts to call these APIs. So I'm just creating a test model here. So you'll see that now I have created another entry in my catalog. It's a test model. Now in the next API, I can show that I can update this. So if I update it, okay. I have to give the ID here. So curl update and JSON. 1 second.
And I just wanted to mention that while the user of the API would probably use something like the notebook or a interface which calls these, the reason for we are showing these command line APIs to show you under the cover what's happening. You probably would not be using this directly. All of these interfaces will be hidden behind other interfaces, either a Jupyter notebook or another package which calls the software and makes it more user friendly and consumable. But
Yes.
for the sake of the catalog operation, wanted to show you the inner details.
Yes. So for example, if I want to retrieve this catalog. This model, I can just do this. Actually, I can print it in a better format so that it's readable. And then also you can list all the possible models that has been saved. So if I do the list, you will see all the models that is there. And it's huge because we have two models and the object, this metadata is like huge here. So these are all the API supported, and also as we know, we can delete the model. So if I want to delete the model, I can delete this model. And then if I try to retrieve it, it should not show me that model. Yeah, item not found. So going back to my presentation. So these are all the APIs supported at this point, and also it will be supported by a CLI at the later point of time. And so the repository where you can find the code that is being used here is the link is provided here. And at the beginning of the presentation, Dinesh mentioned that we have a conference paper. So here is a link to the conference paper that was published in SMC 2022, and also the whole GitHub for the enterprise neurosystem that also hosts many other applications that is there for the enterprise neurosystem is in this github.com enterprise neurosystem. So with this, I'll give it back to Dinesh.
Okay. Thank you, Ananta. So Ananta showed a simple demonstration use case of what the catalog is capable of doing. And what I want to do in this section along with Abhay is talk about a few other use cases that can be enabled. The first use case that this catalog can support, additional use case that catalog can support, arises in the context of mobile or multi-access edge computing in 5G networks. The MEC technology, which is known by various other different variants in the cellular network space, essentially allows you to break out information at a location much closer to the cell tower. To explain what happens, let's consider what would happen in a 4G or 3G network if you have something like a phone or a IoT sensor, a camera, etc., which is collecting information from a location and you want to process it. Effectively, what happens in 4G and earlier networks is that your connection from any of your end device, which includes your mobile phone, to your server treats the entire cellular network as one big physical layer pipe. If you think of your home network as connecting to the Wi-Fi router, the Wi-Fi router, if you try to do IP ping or trace route, the first hop you see is the Wi-Fi router. If you try to do the same thing on a SIM connected cell phone or IoT, you'll see that the first router that responds is a router deep inside the telco packet core. So you will see all the cellular traffic from AT&T going to some sites in Dallas or New Jersey, all the packets from Verizon going to some site in Baskin Ridge, and all the packets from, say, T-Mobile or Sprint going to some site in Kansas City. And it's one big fat connection that goes out there. What happens also is that because of that one big fat connection, if you go any type of processing or say of an IoT device to a device in an IoT platform, say running in IBM Cloud or any other or Amazon Cloud, you would see that the latency typically is 40 millisecond over the network and 100 millisecond all across between the client to the server. In 5G network, what they added was something called a breakout capability, or which they call MEC, again known by various names. So what this would happen is that if you have got a device at the 5G here, say in a building which is in a commercial building, say the one building of IBM, when you send the packet out in the 5G network, the 5G network is capable of taking that system out and sending it to a server which is running right near the cell tower. Now, if you think of how much round trip latency happens between the device and the router here, it probably will typically be a few milliseconds, 4 or 5 milliseconds. The router application could be running within the control of the telco, so underneath the telco firewall, or many of them also give the ability for the commercial provider to run the firewall at the edge server itself. So that allows you to now run the things which 5 millisecond, 10 millisecond latency. So a lot of processing which would be not be done in real time, or which will require sending large amount of data over the internet, can now be processed within the commercial building itself. Now this creates an immense opportunity, say, for processing images from everything that's originating from a building at a server within the building itself. It provides privacy, and more important, it saves a lot of data throughput and data information. But it also is not without its problem. Can we go to the next slide, please? The big problem that this edge computing then introduces is that is that you have many of these MEC servers. So if you think of how many cell towers a telecom provider has, a telecom provider has like several tens of thousands of cell towers throughout the building, throughout the country. Uh, and as opposed to doing a server where everything is processed in a single location, now you're trying to process things which are distributed at many different locations. If you consider these MEC capabilities run by enterprises, a typical enterprise would have, say, a few hundred buildings, and you need to manage, coordinate the software that is running at each of these 100 buildings. So what happens with them is that at each of these MECs, if you want to train a model and say you have got a robot running around at each of the building, and the MEC server at the center is processing the images, you need to send the images over to the model for processing them to all the different MECs. It would be nice and easy if every MEC was using the same model, but the ambient conditions in the buildings are different. Some buildings may be also sending the robot over to monitor images that are dealing with that of a fire extinguisher. Another building may be sending the robot over to look at their images of their building, of their infrastructure. Is there a crack in some of the systems? A third building may be using the robot to monitor the health of the road surfaces. Because everyone is different, everyone would have to have a different model distributed. Now, of course, models are best trained in a central place where you've got a lot of CPU, a lot of GPUs, but you want to be able to distribute those models to the MEC servers in an intelligent manner. And the catalog essentially provides a mechanism to do that. The catalog acts like a place where each the publisher, those who are training the models, and there could be more than one model trained in the cloud, publish to the catalog. And now each of the MEC servers, based on their metadata that's provided, can retrieve the model from the catalog and thereby customize themselves to the appropriate needs that they have for the server. Next slide, please. Okay, so now let's go to another scenario, which is very common in enterprises who are using distributed systems, or even collaborating across different across organization, and which is the need for federated learning. There's a book on federated learning, which and its various use cases in business scenarios. I would just say that it arises in across a wide set of industries. What is the basic problem in federated learning? The basic problem there is that the data which different companies collect, or at different sites that collect, is often very sticky. It cannot be moved easily across site. And the movement of the data across sites is restricted sometimes by data volume, sometimes by the regulatory requirements that you have on the data. So for example, if you just consider a telecom provider like which operates in India and also operates in Nigeria and South Africa, the governments of the two countries don't want the call data records to be shared outside the country. If you consider a bank which operates across multiple national boundaries, the governments don't are not very happy when financial records of their consumers cross their administrative boundaries, and they want to strict controls on that. Same situation arises if you've got two companies collaborating. They want to share data, but they only want to share data in a limited way. Or when two military, say NATO countries collaborate together to create shared models, they again have got severe restrictions on how data can move. So the goal of federated learning then is that instead of moving data across different things to train a model, each of the companies, each of the groups train their own models on the data, and then you combine the neural networks. Now, combining the neural networks is a little bit of a tricky problem, but that arises in many cases. In a particular case, if we just look at the laboratory environment, suppose two labs, they both generate huge amount of data sets. And for example, some of these physics experiments creates terabytes and terabytes of data. Moving terabytes of data across labs is difficult. Whereas if you train a model on that, and the model would be a few megabytes, or if you train a really large model, maybe a gigabyte, a few gigabyte, moving that data and combining them is often much more efficient than trying to move terabytes of data. Now, federated learning is the approach that helps. Let's go to the next slide to take a quick look at how federated learning works. So if you look at how traditional lab learning, machine learning, and neural network works, they take a big piece of data, they divide it into small batches, the mini batches. And essentially, each of the neural networks starts out first with some randomly selected weights. They optimize the weight on a little bit mini batch, see how much they're off from the answer on the full data, and then they basically retrain themselves on another small mini batch. So essentially, iteratively, each of these weights are modified and computed till they basically come to a answer which is much close, or the error rate that is acceptable. In some sense, you can say that it's like the traditional, say, Newton-Raphson method in trying to find the roots of equation, where you keep on trying and trying to get better estimates till you get an acceptable answer. Now, in federated machine learning, the same trick is used, except the trick that is used is that the mini batches, instead of being taken from the same data source, a small number of mini batch is taken by each of the labs. So lab 1 will take the first mini batch, lab 2 will take a second mini batch, lab 3 will take a third mini batch, and so on. They all train their weights, and then they send it to a fusion server, and the fusion server averages and aggregates that model, sends it back to them. And now they have got an average weight, which is sort of like training it on a mini batch consisting of the mini batches of each of the labs. You integrate them, and then you can repeat the next process. Now, in order to do that, there are a few things that have to be coordinated. First, you all have to have a common model architecture. You all have to have a common data normalization approach, etc. And these are all independent digital assets. So the way that the catalog is used to train the federated learning model is that the Fusion server will publish in the catalog the architecture description, the normal data normalization or averaging parameters, etc. Each of the agents, each of the labs picks that up from the catalog, and then they train their mini batches, create the model, and publish the model weights into the catalog. And as they publish the model weight, they also publish their rounds. And when as the rounds is published, the Fusion server picks up all the models with the round numbers, searches for them, aggregates them, and publish it back in the catalog for the labs to pick it. The use of a catalog as an intermediary acts as a good way of coordinating all these different agents, because some of the agents may be slow in publishing their data. Some of the agents may have intermediate failures that they would be restarted. And having an intermediary catalog provides a much better approach to accelerate, expedite, and simplify the operation logistics of having federated learning. So those are the two use cases. I'm going to turn it over to my colleague Abhay to talk about a third use case in which the catalog can be used. Abhay, over to you.
Thanks, Dinesh. So in this use case, what we are looking into is discovering the assets from the catalog. So what's happening is over the time, the machine learning assets like models, data sets, and all those will be increased, and we will have a lot of assets into the catalog. So we have to provide a search functionality. I'm saying here like a basic text related search. But with the assets, there are different types of assets. Like as we have seen in the previous example, the shared assets with a particular organization, and maybe the assets owned by that organization. but there is a kind of a rich set of open assets too. So the idea here is to get access to those open assets by means of, let's say, crawling and converting that all the available open assets into the format which is suitable for our asset catalog. So we will have a kind of some process which looks into the major sources of open assets, convert them into the format that we can ingest into our catalog, and maybe the format which is better for better for searching, the text-based searching. And there will be an kind of providing an interface where one can go easily and search different types of assets based out of different query parameters, and have the assets listed into the some kind of a result page. One thing to consider here is there would be like different types of asset is authorization policies and all related to the assets that we can consider while building this. But having a kind of a asset search interface is a kind of one of the use case of the asset catalog. Okay, so maybe yeah, that's one from me, and I will turn it to the Josh maybe to.
Hello, I'm Josh. I've been working on the catalog, and on this slide you see, so we've had an existing implementation that we put together. It's kind of like a prototype, and in Anandita's part of this discussion, you saw a little bit of the different operations that we have available. This slide focuses on that implementation and what we have done to get there, and then also some of the reasons why we've decided that we need to go to another approach that I'll talk about in the next slide. So this current approach has multiple containers, and we create a CLI in Go, and then we spin up the containers, and there's one container that has the CRUD operations that Anandita discussed, and then also another container that contains the actual database that we're communicating with. This is really a common approach for getting something up and running quickly. But one of the problems we have is we're focused on, you heard a lot about the different use cases and the uses of this catalog. We want to have something that will scale and be able to be used by as many people as possible quickly. And then also interoperability is a very important part of this. So some of the issues we ran into, as you can see on the slide, our current implementation is a prototype, so we haven't done a lot in terms of security. Another thing is that scalability. It's up to the user of the CLI and the rest of the catalog to spin up the environment. One of the reasons it has been difficult for us to go from this environment to something better and more scalable is because lack of resources. And so, by the way, this is a plug for if anyone watching this recording or in this presentation is interested in joining, please let us know. But and then the other thing is making sure that this kind of goes in line with the scalability argument, but making this available as a service that everybody can use. If you go to the next slide. In order to get from our current implementation to a new implementation that checks off some of those requirement boxes, we are wanting to go towards GitHub. It is a very scalable, very popular service that everyone has available to it, and it follows an API in two different ways that is very generic and easy for everyone to use. One is the GitHub API. So they have an API that's available that's via REST, and everyone can make use of that API for free. GitHub itself is, and then before I get into GitHub, the other API is the Git itself. So Git is a command line, it is a way for handling assets and source code of any type. I'm sorry, Anandita, I think we lost the presentation. Oh, thank you very much. And so GitHub is based on Git, right? And so Git has a lot of features built into it that makes that you can just use against any of the GitHub repos. So the other benefit of going with this approach is that GitHub is very popular. It has a ton of different repositories available out there already. And the way that we are, I'll get to this in another slide, but it will make it very easy for us if we make use of the GitHub CLI with their API to access a large amount of assets that we could already tap into. When you heard Abe talk about the discoverability, many of the assets that we could discover likely already exist in GitHub. So targeting GitHub as our first implementation in what we're describing here makes it more likely that we'll be able to discover the assets. So that pretty much covers this slide. If you can go to the next, please. Great. So this is labeled operations, but it's really focused on the schema of how we can look at a repository and know, instead of it being just some Python app or whatever anyone decides to upload to GitHub, it's actually an asset within the catalog. And the way we plan on doing that is making, so in a GitHub repository, or any Git repository for that matter, you have the ability to add metadata to the repo. In GitHub in particular, you're able to also do things like add in tags. And so when you use the GitHub API, you can then filter down the assets that you're looking for based on those tags. And another feature is that when you have the folders, so every Git repository is just a folder structure, basically. And so we would be looking for different files within the GitHub repo named in a certain way to know that that would contain more metadata for the assets, so that we can do things like understand the way this asset is used. In the catalog, we'll have multiple different types of assets. So we'll be able to verify what type of asset this repo is related to. And then also, more importantly, there's assets will be associated with each other. And so we'll be looking at this metadata to determine how these different assets are connected to the broader community. Whether that's based on versioning, which Git is very, that's built into Git itself, or if it's just connected to a certain type of asset that is important for the project that is using the assets. And this, we're giving some details here based on like the metadata, the specific metadata. It's important to note that this is really what we are focused on at the moment, and very subject to change, but we're defining this based on our engagements with different projects that are interested in enterprise neurosystem, and coming up with a more or less generic model that tries to fit the widest types of assets possible, so that we can have this would be like a generic schema for multiple different asset types. And then any individual asset could potentially have its own separate schema that further defines that asset as needed. If you could go to the next slide. So the CLI operations are, when Anandita gave the demo of the demo that she gave, she focused on the CLI operations: create, remove, update, and delete. So in the future implementation that we're talking about, GitHub has a CLI, and they have this extension capability that you can use, that you could create an app that is in the format of an extension based on Golang, and then that would be where our CRUD operations live. And then I think that's the only thing that's different from what you saw in Anandita's is the search capability. So, and this kind of relates to what Abe was talking about in his presentation. So the search capability would be provided by the GitHub API and first-class citizen of the GitHub CLI. So whenever we create an extension, we would have a function call to call into the to get details from the GitHub repositories. And if you go to the next slide, please. And I guess that's it. Dinesh, you're on mute right now.
So thanks everyone for the presentation. Let me open the floor for any questions. If any of the people have any questions or comments on the different parts of the presentation.
Question. This is Sanjay. On the last part of this presentation, if GitHub is being used to store the assets, then how do we handle private models and privately shared models? Because that's really one of the key things we're trying to work through. That was shown in the use cases where ORNL and Slack wanted to share like particular models, for example.
No, absolutely. So the thing is that the GitHub is a public service that's already available. So this service which is available allows anyone to use a public repository to share models. In many companies, for example, IBM, which uses GitHub for its own private thing, the same private instances of GitHub are there. So a private instance of GitHub can be used for this model. Also unstated in the future evolution was that we are not targeting just GitHub, but we're also targeting other sources like IBM Cloud Object Store or Amazon S3 or Box or other means of storing medium. Our goal here is to go to an existing service which is already up and operational and allows us to store objects as opposed to trying to create our own Mongo or any other database. So that's the goal. And one obvious way would be like just use a private instance of GitHub.
Okay, so that makes sense. That there are other object stores that are being targeted.
And another part of that answer is private repositories. So a lot of organizations, including my own, use GitHub extensively, but almost a good portion or a good portion of projects that are internal they're all private. Right? So you could have your assets be private, still in GitHub though, and make use of the GitHub CLI so that it would only be accessible from people within your organization or people that you specifically added to the project.
Right. And then, which leads to the cross-enterprise problem, right? Which would be very interesting, which is, I think, leads to what Dinesh was saying, which is some of the other storage mechanisms might be possibilities in the future.
Yeah, and this is something that we have this current implementation that's just a Docker container. I think what's important is that we get the definition of what if there's a repo, an asset that is a part of a repo, and as long as we make sure that the definition of that asset, the files that make up that asset in the repo are correct and universal, right? Well, then that could be a repo in your local Git repo, and then you just point there. And as long as we have an implementation that is able to target, either Git or other places where you can store data, then we'll be able to have the same functionality that we have in this GitHub extension be used to target that. And so that's so the benefit is that the extension is just a Golang application. It's not, the only thing that makes it be a GitHub app is when we call the functions that GitHub provides us. And that's not, and we already have these other functions that are able to call out to, in this case, MongoDB, but that could be anything.
Okay, so you could actually have some models in one private repository and other models in a different private repository then. And as long as you had access to all of them, it would work.
Right. And one thing that we're still investigating, but we haven't fully 100% verified, is making sure that from the GitHub extension that we create, that will have access to these other sources of data. I don't see anything stopping us from being able to do this. I just haven't actually verified this yet.
Okay.
So if, say the worst case scenario is that it does make some type of weird restriction on what sources you can get data from within the GitHub extension ecosystem, then the functions that we make available in that GitHub extension will only be for GitHub, but then we'll just continue to have our own CLI that you can use. And the GitHub extension would just be for that. I don't know if that's a limitation of the GitHub CLI extension ecosystem or not. I don't think it is. It seems kind of far-fetched, but that's where we're at today.
Okay. Are any other questions?
Follow on to the same discussion, Dinesh. So in your presentation, you mentioned about like data being, distributed across and being stays where it is, at the same time having that federated learning capability with which you just take the smaller chunks of data in that is required for the model. Will this also fall into this GitHub extension?
Yes, indeed. All the applications and use cases should work with any version of the catalog implementation. What changes across the catalog implementation? The API remains the same. It's just that the second version or the evolutionary version of the catalog that Josh described would be easier for people to use. It will be easier if you look at what the first instance of the catalog did. It basically exposed the same API, but to get it operational, you have to find some place to run those containers and then retrieve, install, and run those containers in two different places. In effect, one has to create a service even though the code and containers are readily available. In the other catalog, for access to the thing, we are using and leveraging an existing up and operational service. So that will just make the process simpler and easier. And as Josh mentioned, if we keep the API and the standard the same between the two versions of the catalog, all the applications and use cases should be able to run seamlessly across like both types of catalogs.
All right, thank you.